Definitions of vibrational optical activity. I just want to start with the very easiest thing. Optical activity comes in two forms. You all know optical rotation, and then there's circular dichroism. Optical activity is the difference in the index of refraction for left and right circularly polarized light, whereas circular dichroism is the difference in the absorption of left and right circularly polarized light by chiral molecules. And they all can be lumped together as a complex refractive index, and they're related by mathematical transforms. So the ORD spectrum has the same information as the entire circular dichroism spectrum. So that's the way things stood up until the early 1970s. And then in 1973 and 74, VCD and ROA came to the scene with first measurements, and I'll tell you a little bit more about that. This is just the definitions of VCD and ROA, and the main idea here is that they both start in the ground electronic state and go to the first vibrational level of the ground electronic state. And with VCD, it's just a direct absorbance, and you're taking the difference in the intensity between left and right circularly polarized light. And for ROA, you have more freedom, and you can modulate either the incident circularly polarized light or the scattered circularly polarized light, or both. And these are the definitions spelled out in terms of intensities. VCD is left minus right absorbance, and ROA is the other way around. It's right minus left by convention that was started by Laurence and we've all stuck to through today. There are four different forms of ROA. I won't go through them except to say that ICP was the original form discovered in 1973, and SCP is the form that's commercialized today. And I'll say a little bit more about that in the rest of the talk. So this is just a brief bullet history, very short history of VCD and ROA, just to show how parallel their developments were. VCD was discovered by George Holsworth at the University of Chicago, and there were several other collaborators, including Al Moskowitz, who was my undergraduate advisor at the University of Minnesota in 1964 to 67. But that paper came out in 74, and we confirmed that first observation of VCD in 1975 with Jack Cheng, and then Tim Keiderling joined our efforts for a major paper on VCD in 1976. Fourier transform VCD was first published in 1978, and both Max Deem, I'm not sure Warren Vedrini's at the conference, but I talked to him earlier today, participated in that. That took place actually at the Nicolay Instrument Corporation in Madison, Wisconsin. Then you have to fast forward almost 20 years to get it commercialized by BioTools, and now there's a second generation. For the ROA, it was discovered by Laurence Barron and A.D. Buckingham, and Bogart was a postdoc, and it was confirmed by Hoog in 1975. We made the first measurements of the SCP form of ROA, which was the second one I showed you, in 1988, and then was commercialized in 2003 by BioTools, and there's a new generation of instrument. So these are the molecules that are normally used or measured by VCD and ROA, and VCD has a few more. It's a bit more versatile than ROA in terms of sampling. But basically the differences between VCD and ROA are almost the same as IR and Raman. IR is really great with organic solvents, and ROA is better for aqueous and biological samples. But if you just scan that, you can see some of the differences and similarities. They both can be calculated accurately with quantum calculations, density functional theory these days. And the ROA has other variants. The ROA has a lot more possibilities for different configurations and polarizations and enhancements that are not present for VCD. So I think that ROA will be a rich development long into the future with many possibilities. I've written a book that covers all the basic aspects of VCD and ROA. So let's talk about the discovery. And I'm showing you these just not only for historical purposes, but to show you how kind of shaky things were at the very beginning. The Holsworth discovery of VCD is right here. It's just a single vibrational mode in a molecule that has one lone CH stretch at the chiral center. And this came out in January of 1974, and in September of 74 we were able to finalize the construction of our instrument, and we measured that spectrum to confirm this spectrum. But at the same time we saw other vibrations, the OH stretch, indications of the phenyl stretching, and reported that. Then 3 months later, we submitted with Tim Keiderling a huge paper on VCD. We were just running around grabbing everything off the shelf that we could. These are other vibrational modes in that first molecule. And then these are all the molecules that got put into the first full VCD paper that was published in 1976. And I'm showing the instrument diagram for a couple of reasons. It has lots and lots of lock-in amplifiers, and there's an auto circuit. To do the IR with a dispersive instrument, you need a light chopper. And the light chopper is important to define zero intensity because room environment provides infrared intensity that the detector sees. But this last little loop here was a way of cleaning up the VCD signal coming out of the high-frequency lock-in. And that's because interfering with the output of this is just stray radiation from the room. But if you also pass it through a second lock-in tuned to the chopper frequency, you can clean up and get rid of that RF interference. But this little loop became the core of the idea of how to do Fourier transform VCD, because you can think of a Fourier transform as a light chopper with a chopping frequency for every different frequency simultaneously. Those are the Fourier frequencies. And so instead of having a lock-in, if you just have an FTIR spectrometer here, you can do the same thing. So this is from the USC lab. After I got my position at Syracuse, we dressed me all up. But I wanted to show you all the lock-ins. This strip chart recorder is where the spectra came out. And that's it. Once that's been recorded, until you get it duplicated by an artist, that's all you have. And you have to be very careful. You have to make sure the ink doesn't run out. This is a 4-pen ink recorder, making sure all those pens were recording at the same time, because we simultaneously measured the IR transmission and the VCD. And then we'd go back and run the other enantiomer over it and everything. So it was a lot of work to just spend 2, 3, 4 hours just to run a couple hundred wave numbers. So it was a lot of work. So let's now jump ahead a few years after I was at Syracuse to do the Fourier transform instruments. And Max Diem and I published a theory paper on it, dubbed double modulation FTIR, that also works for linear dichroism. And this came out in Applied Spectroscopy in 1979. And the basic idea is that you take an FTIR spectrometer and you polarize the light, you put it through a PEM, you get modulation sample, and then the lower path here leads to an interferogram of the IR. You just the preamplified signal, you can Fourier transform it to get the IR. And if you send the signal also through a lock-in and synchronize it with the PEM, you can pick up an interferogram simultaneously present at the detector. That's the interferogram for the VCD. And if you Fourier transform that, you have your VCD spectrum. So that's the way the VCD essentially works. You get two spectra simultaneously. And this was the first paper reporting Fourier transform VCD that came out in JACS. And that's with Warren Vedrine and Max Diem. And this is just a calibration to show that it was working. This was the first Fourier transform VCD right there. And this was a corresponding dispersive of the same measurement. And you can see it's kind of shaky signal-to-noise ratio. This is showing that opposite enantiomers have opposite FT-VCD spectra. So it's just right on the ragged edge, just like the first measurement of VCD, but A few years later, we published a paper in Chemical Physics Laters with Elmer Lipp, and we were able to get in the mid-IR beautiful spectra, just stunning spectra with unprecedented resolution, and this became the basis of commercial VCD. And now, jumping ahead 20 more years, we finally have BOMEM manufacturing the first VCD, Fourier transform VCD instrument. The first customer was my postdoc advisor, Phil Stevens, and I have a few historical slides. First of all, this is just the layout. What was unique about it is it had two sources. These sources interfere negatively for the transmission, which helps you avoid saturation, and they interfere positively to almost not quite double your VCD intensity against a constant noise background. So this was a big boost when we plugged that in and compared it to single mode operation. This is the FTIR spectrometer 2 days before its first use. The detector hasn't even been placed in the instrument yet, but the interferometer is back here. The beam comes along the side, goes through the PEM, and then through the sample chamber and is detected. So here are all the proud contributors to the first VCD, commercial VCD measurement. And this is Henry Beisch, who is here at the conference today. His son, Thomas Beisch, and J.R. Roy, who is now the president of ABB, and Alan Rilling was the engineer, and my postdoc, Fujin Long, who came earlier to set up the VCD measurement, help set it up. This is the first FTIR VCD spectrum, and compared to the first VCD spectrum, this is just breathtaking. This is a 10-minute measurement with no baseline correction, and we were also excited and happy to see this. I mean, it required virtually no alignment. It was just the way it came out, and we all signed the first sheet, including Rena Decor, who took the last picture, but she was one of the, I can't remember what you said there, but Rena excited or something like that, so which is always the case. No news there. So this is the first installation. A few months later in the laboratory, Philip Stevens. That's Philip Stevens. The other two characters I think you know. And now we're just going to move a little bit ahead to another advance that took place a few years after the commercialization, which was polarization scrambling with the dual PEM system. This was published in Applied Spec in 2000. And the idea was to add a second PEM, a second lock-in, and to subtract the interferograms of the two lock-ins before even any further processing. And this got rid of baseline instabilities and baseline birefringence, which advanced and further stabilized FTVCD measurements. So that's a layout. So you're just adding a second PEM and a second lock-in. But you have all these lock-ins that are taking place. And this shows you just by turning on the second PEM, you can change that baseline to this baseline without the second PEM. To go from there to there might take several days of optical adjustment. And we were all used to having to do that. And when we had a dual PEM system, it changed our lives. So this is the dual PEM setup on a side rail. There's the sample cell and the liquid nitrogen-cooled MCT detector. This is the way it looked out as a final commercial product with the dual PEM. You can see all the lock-ins and filters and PEM controllers. And I actually want to go back and say, when we first did this, this second PEM did not belong to me or Rena, but it was donated by Heinz, and just as a temporary loan. And I think we still haven't returned that PEM yet. Thank you, Paul Heinz, for your generosity and help in getting us started on dual PEM VCD. Paul is in the audience today. So this is the first installation of VCD in a pharmaceutical company, and then they went right to the dual PEM setup. This is at Wyeth with Oliver McConnell, who was an administrator there and not a spectroscopist, but not that much, and he went on to do his own VCD calculations, and so was really happy to have that instrument. So what's going on today in terms of technology? Well, the whole thing is now reduced to one box and a PC. And there are no lock-ins. it's all done by time sampling in the megahertz region, and interferograms, the 3 simultaneous interferograms, are achieved by numerical interpolation on the fly as the interferometer scans. Detector hold time went from 4 to 6 hours up to 24, which is why there's such a big dome there. It's a big, tall detector. So you can essentially run 24/7. There's 2 PEMs, 2 sources. There's a PEM there and a PEM on the other side of the sample, all under one enclosure and a rotating sample cell. So this just to tell you that if you add a rotating sample cell to the dual PM setup, you can do solids and get rid of a final source of artifacts. So this is what a VCD spectrum looks like today. There's 2 enantiomers of camphor, the same IR spectrum, the racemic and the noise level there, and then equal and opposite VCD. There's no particular correlation between strong IR and strong VCD, and this is 4 orders of magnitude down. But it's 5, 10, 20-minute measurement, so it's not that hard to get at all. It just pops right out. I'm going to switch now to ROA, tell you a little bit about ROA. This is a paper that we published in 1988 reporting the first circular polarization measurement of ROA, and that transformed itself 15 years later into a BioTools product, and it sort of looks like this is the basic idea. It's based on a design published in 1999 by Werner Hug, who worked very closely with this and with Critical Link in Syracuse to manufacture and come to a final design of the ROA spectrometer. And there's a laser underneath and a spectrograph up above and fiber optics below, and the diagram, which is quite simple, you can see, is got basically a laser excitation rail where you get rid of all the polarization going into the sample, and then coming back out, we have ways of separating left and right circularly polarized light, converting it to linear, orthogonal linear states, splitting it with the beam splitter. So we're actually measuring left and right circularly polarized scattered light at the same time. And then it's just numerically we add and subtract to get the Raman and the ROA. So for ROA in SCP mode, there's no need to modulate back and forth between left and right circularly polarized light. It's measured simultaneously. And here's an ROA spectrum showing equal and opposite ROA spectra, just like for VCD, alpha pinene. And it's 3 orders of magnitude down. It's a bit bigger than VCD relative to the parent because it's measured in the visible where the wavelengths are shorter and the optical activity is proportionately larger. So we also developed a dual circular polarization method. I showed you those options on one of the first slides. And we actually measured dual circular polarization ROA and compared it to the ICP in this paper with Lutz Hecht and Diping Che, who were pioneers in this form of circular polarized ROA. And this is a very recent paper with Honging Li, who I believe is in the audience, at BioTools. And these are all simultaneous measurement of all 4 forms of ROA by converting the chiral Raman into 4 circular polarization mode operation. So this is sort of the activity of VOA these days. For VCD, there are approximately 75 commercial instruments out there all around the world. And on the arena check the other day, something on the order of 125 papers published last year, over 1,000, maybe now it's 1,200 or more total VCD papers published. ROA is between VCD and ROA, there's always a factor of 2. And to buy it, it's a factor of 2 in price. You can guess which way it goes. For a number of papers published, it's a factor of 2. For the number of instruments, it's close to a factor of 2. So it's always there. It's growing very similarly in parallel to VCD, but it was commercialized later. It's more complicated. It's more delicate to measure, but it also is richer in total information content. So there's a lot of momentum going on. Here's the number one application, determination of absolute configuration. There was a focal point article published in July of 2011, and Nafie was a graduate student of mine at Syracuse who now works at BioTools. And the idea, is you measure the VCD and you do an ab initio calculation. You compare the calculated and measured VCD, and when they match, because you know what you put into the calculation, you know what the absolute configuration is. And this is a new way of doing that. You don't need to crystallize the sample. You can use just solution phase sampling, and you compare what you measure to what you calculate. And there's commercially available software from Gaussian. So these are details if you want to do it, but it can be done on a beefed up PC that's probably, $3,000 is all you need to do to buy a really hefty PC these days to do VCD calculations, easily one a day. So here's an example from quite a ways back, 2002, with Edwin Kellenbach when he was at Organon. And we actually did the calculations before we were comparing the measurements. And we went to their lab, and lo and behold, it was almost a perfect match. So this is the minus is the measured VCD of the minus rotating optical rotation enantiomer, which you physically have in your hand. This is the R configuration. That means the hydrogen is pointing up. This is the absolute configuration, the optimized geometry from the calculation of this molecule. And it's just a question of whether that hydrogen is up or down. And we nailed the absolute configuration and published the results. But that's a very simple example to show you actually the state of art of DFT. You can essentially calculate beautifully IR and VCD with no adjustable parameters. Your choice of basis set and bandwidth is all you have to do. We also, this is just kind of a curiosity, with Rosina Lombardi, I published a paper in Chirality in 2009 where in addition to VCD and IR, we added the optical rotatory dispersion spectrum, or the vibrational circular Birefringence. So this is the oldest form of optical activity. The first measurements were in 1811 of optical rotation. So this is VCD of optical rotation, and just by changing the bandwidth from absorptive to dispersive, we were able to calculate this ORD spectrum, also the VCD and the IR. And the difference, there are three different calculations, and the one that's in blue is double zeta, and triple zeta are black and green. You can see that the black and green match experiment better than the double zeta. So if you beef up your basis set a bit, you get closer agreement with experiment. Now this is just a little timeout. I'm not going to dwell much on the theory, but just to say that for IR, it's the square of the change in the electric dipole moment with nuclear position. You all know this. If you're doing IR spectroscopy. For VCD, it's the dot product of two transition moments, the electric and the magnetic dipole. But the magnetic, the derivative is with respect to nuclear velocity or nuclear momentum, not nuclear position. If you use nuclear position, you get zero. So because of the Born-Oppenheimer approximation. So you need velocity properties. And we've worked out the theory of velocity properties of molecules. This is the ordinary density, and this is where the modulation of the density is where IR intensity comes from. But there's no zero-order term for the current, which is the corresponding velocity. So electron density moving through space creates a current. And you need to take what it is correlated to, it's correlated to the velocity, r dot. So there's a correlation between when the velocity is zero, the currents are zero. So in the Born-Oppenheimer approximation, when the velocities are zero, the nuclei are fixed, there's no current. But we've shown formally through first-order perturbation theory that these two things are equal. The conservation law of current and charge density into a volume of space is conserved and equal. So the gradient of the current going into a volume element, this is beyond the Born-Oppenheimer approximation because it's r dot, is equal to the Born-Oppenheimer version. And we've actually plotted current density for, you've all seen normal modes expressed by displacements of nuclei, but you've probably never seen what the corresponding velocity maps are for current density. And what's interesting about this is that this hydrogen, this is just formaldehyde, this is an oxygen. When this hydrogen goes in, there's a little bit of back recoil from the carbon, and this hydrogen comes out. You can see the flow of current, electron current, across that boundary, but there's also a circulation of current up here at the oxygen, which creates a magnetic dipole. And there's no way to see that just by doing normal Born-Oppenheimer calculation, because there's no change in local density here. It's just a circle and just feeds into itself, and there's no evidence if you look at the density change map for the mode. So, and you can also see VCD intensity by looking down the direction of the electric dipole transition moment, and the magnetic is any motion in the plane perpendicular that creates a magnetic moment parallel or anti-parallel to the electric transition moment. So I just wanted to show you these little pictures that can come out of VCD theory. So let's go on and do applications. VOA in pharma and biopharma. These CNE News articles are really what allowed Rena to convince BOMEM to build the VCD for the first time, because we just did, a market study on the fact that chiral drugs were going to be becoming important, single enantiomers were going to be becoming important. You had to prove absolute configuration, and BOMEM luckily saw the prospects of doing that and agreed to help Rena and I to go ahead and start BioTools and start commercial VCD. So let me see, I'm going backwards. So these are the companies that currently use VCD on a daily basis. They either have their own VCD spectrometer or they're outsourcing it to BioTools or somehow getting calculations done. So it's a pretty comprehensive list of pharmaceuticals. There's also ROA on there. Amgen has 2 ROAs, and you can see ROA sprinkled around. And there are a number of companies that are now wanting to get ROA, mainly for biopharmaceuticals, and I'll show you how that's working. Okay, now my little light has gone on, so I'm going to speed up a little bit. This is absolute configuration paper, just showing that you can do this for molecules with more than one conformer, that you have to add the contributions up. And I wrote a review article. These are a variety of molecules. I can't show you all the pharmaceutical molecules because they are confidential, and so there are just a few that are published. But there are many, many, many natural products, and all of these have had their absolute configuration determined by VCD. And then for biopharmaceutical applications, VCD and ROA can distinguish secondary structures of proteins, and these are this is VCD going from alpha helic to beta sheet, and you can see the changes in the VCD spectra, and these are the corresponding ROA spectra. ROA is probably even more powerful than VCD for protein, not only for secondary structure. This is just showing that you can do PC maps in 2 or 3 dimensions to segregate kinds of folding in proteins. And then this is a study by Tien-Jin Lee and Amgen showing that there are sensitivities in ROA that are not present in Raman. If you stress a protein between pH 3 and pH 7, for these immunoglobulins, IgG1 and IgG2, there's no change that's discernible in the Raman, but the IR have a tremendous change between the naturally folded form and the stressed form. And so ROA has a sensitivity that exceeds that of any other spectroscopic technique that we've been able to study so far. And I'm going to close with just a section on enhanced VCD. There's many different ways to enhance VCD, but the one I'm going to pick is the one on protein fibrillization and development. You may know that fibrils form from proteins when they're destabilized and form a long beta sheet chain where the strands are perpendicular to the growth of the fibril axis. And fibril filaments, which are the individual strands, these are 4 different filaments, can braid and twist. And when they do that, when they form and braid and twist, the VCD grows by 1 to 2 orders of magnitude. And this is a paper that first reported that. These are 2 different proteins that give virtually the same VCD spectrum. This is comparison of lysozyme and insulin, have remarkably different VCD spectra, but as fibrils, they have almost identical intensities and very nearly the same relative intensities. And you can also follow fibril development with time, just heating, watching the fibril grow while almost nothing happens in the IR. So this is extraordinary sensitivity of VCD to fibrils. We also found that they completely reversed. If the twist reverses, then the whole enhanced VCD spectrum turns upside down. And this is a remarkable discovery that is now being used to study the effects of fibrils. And so I'm going to skip ahead a little bit. We can control the chirality of fibrils, high pH and low pH, and control which way these fibrils twist. And then we also were able to relate the fibril chirality of the filament to the individual morphology, whether it's a twisted fibril or whether it's a flat fibril. And the morphology fibrils with different morphologies do have different disease characteristics in terms of their effect on cells. So we're trying to see to what degree the danger of fibrils is related to their chirality. So I'm just going to close with the following conclusions, that VCD is a sensitive technique for all kinds of classes of molecules. VCD and ROA have evolved over the past 40 years from modest beginnings to routine spectroscopic measurements in academic and pharmaceutical and other areas. I showed you a little bit about velocities and a little bit about enhanced VCDs. So I think with that, I'd like to thank the following institutions for financial support, and I'd finally like to thank you for your attention, and again, SSP for this award. Thank you very much.